We have already seen that Euler's theorem states that if GCD of A and M is equal to 1, then A raised to phi of M is congruent to 1 modulo M. But from the proof of Euler's theorem, we can also see that lower powers of A may also be congruent to 1 modulo M. To show this, let us assume that L is the LCM of phi of P1 raised to alpha 1, phi of P2 raised to alpha 2, etc. Phi of PR raised to alpha r, where the prime factorization of M is P1 raised to alpha 1, P2 raised to alpha 2, etc. PR raised to alpha r. Then L is the least common multiple of each of these numbers. So we can see that for I varying from 1 to r, L will be equal to phi of Pi raised to alpha I into some integer, say Ni, since L will be a multiple of each of these numbers. So there will exist some integer Ni satisfying this relation. Now, from the proof of Euler's theorem, we have the congruence relation A raised to phi of Pi raised to alpha I is congruent to 1 modulo Pi raised to alpha I using case 1 from the proof of Euler's theorem. Here, if we multiply Ni copies of this congruence relation, then we will have A raised to phi of Pi raised to alpha I into A raised to phi of Pi raised to alpha I, etc. That is, if we multiply Ni copies of this congruence relation, we will have A raised to phi of Pi raised to alpha I into Ni congruent to 1 modulo Pi raised to alpha I. That is, A raised to L congruent to 1 modulo Pi raised to alpha I for I varying from 1 to r. So, A raised to L is congruent to 1 modulo P1 raised to alpha 1. It is also congruent to 1 modulo P2 raised to alpha 2, and so on. A raised to L will be congruent to 1 modulo PR raised to alpha r. Since these prime powers P1 raised to alpha 1, P2 raised to alpha 2, etc., PR raised to alpha r are all relatively prime to one another, we will have A raised to L congruent to 1 modulo product Pi raised to alpha I over I varying from 1 to r. That is, A raised to L congruent to 1 modulo M itself. Thus, we can see that a lower power of A, namely A raised to L, is also congruent to 1 modulo M. Here it is easy to observe that L will be less than or equal to phi of M, since phi of M is the product of all these numbers and L is the LCM, least common multiple of all these numbers. So, L will be less than or equal to phi of M. Thus, we have shown that a lower power of A is also congruent to 1 modulo M. This property can be used to solve many problems. Let us consider an example where M is equal to 105, which can be factorized as 3 raised to 1 into 5 raised to 1 into 7 raised to 1. Here, using Euler's theorem, we have A raised to phi of M, which will be equal to A raised to 48 congruent to 1 modulo 105 when the GCD of A and 105 is equal to 1. Here the quantity L, which is the LCM of phi of each prime powers, 3 raised to 1, phi of 5 raised to 1, phi of 7 raised to 1 will be equal to LCM of phi of 3 is 2, phi of 5 will be 4 and phi of 7 will be 6. Why? Since the phi function of a prime is always equal to p minus 1. So, we have L is equal to the LCM of 2, 4 and 6, which is equal to 12. So, a raised to 12 is also congruent to 1 modulo 105. Now, let us try to prove this corollary, which states that if GCD of A and M is equal to 1 and if n dash is the least non-negative residue of n modulo phi of m, then A raised to n is congruent to A raised to n dash modulo m. This is an application of Euler's theorem. Since we are given that GCD of A and m is equal to 1, we know that A raised to phi of m is congruent to 1 modulo m using Euler's theorem. And we are given that n dash is the least non-negative residue of n modulo phi of m. So, n is congruent to n dash modulo phi of m, which implies that the difference n minus n dash is a multiple of phi of m. Let this be k into phi of m. Now, if we consider this congruence relation, A raised to phi of m congruent to 1 modulo m, and if we multiply this congruence relation by itself k times, then we have A raised to phi of m into A raised to phi of m into etc. A raised to phi of m congruent to 1 into 1, k copies of 1, which is nothing but 1 itself, modulo m, which implies that A raised to phi of m into k is congruent to 1 modulo m. But we have assumed that n minus n dash is equal to k into phi of m. So, we can replace this quantity by n minus n dash, that is A raised to n minus n dash is congruent to 1 modulo m, that is A raised to n is congruent to A raised to n dash modulo m by multiplying this congruence relation by A raised to n dash on both sides. Thus, as we claimed earlier, we have obtained that A raised to n is congruent to A raised to n dash modulo m. Now, let us consider an example. Compute 2 raised to 10 lakh, that is 2 raised to 1 million modulo 77. We know that the modulus 77 can be expressed as 11 into 7. Here, the base A is equal to 2 and the modulus m is 77, and we can see that GCD of m and A is equal to 1. Let L be the LCM of phi of 11 and phi of 7, which will be equal to LCM of 10 and 6, which is 30. Hence, by the remark we made earlier, A raised to L, that is 2 raised to 30 is congruent to 1 modulo 77. And we know that the number 10 lakh when divided by 30 gives the quotient 33,333 and leaves remainder 10. Therefore, 2 raised to 10 lakh can be expressed as 2 raised to 30 whole raised to 33,333 into 2 raised to 10, which is congruent to 1 raised to 33,333 into 2 raised to 10, which is equal to 2 raised to 10, and 2 raised to 10 is 1024, which leaves the remainder 23 when divided by 77. So we have 2 raised to 10 lakh is congruent to 23 modulo 77.